Hello, good afternoon everybody. My name is Geoff Walker and I'm Operations Director for Faraday Predictive here in the UK. Faraday Predictive, well, we're all about predictive maintenance and automated fault diagnostics using electrical measurements on rotating machines like pumps and blowers, etc. The sort of things that I'm sure you have many of. Today I'm going to be talking on how maintenance strategy choices can improve your pump reliability and also reduce your energy costs. The implication of why the choice of maintenance strategy implies there is a choice. It means you can change something. Well, why would you change? When you think across the water industry, many sites are very similar, and it's a relatively slow-moving industry. Right around the world, plant design's conservative. You typically have a duty, assist and standby, so you have inbuilt redundancy. It doesn't really matter if something stops working. The cost of downtime is low. The cost of the water is generally pretty low, and so most, if not the majority of sites, adopt a run to failure or breakdown maintenance strategy. That's not true for most industries. Oil and gas, power generation, critical manufacturing have long adopted fixed schedule maintenance, what we call PM, preventive maintenance. Actually, those industries are trying to move towards predictive maintenance, so 2 generations away from the breakdown maintenance where the water industry is. But they have different economics. Their raw materials are expensive. The consequence of downtime can be much greater. But things are changing now because the massive increase in energy costs is giving a new focus for the water industry. The opportunity to optimize operations to reduce energy wastage. Adopting a condition-based maintenance strategy can not only optimize your reliability and minimize your maintenance costs, if you use the right technique, can also help you reduce energy costs. This talk is titled about the choice of maintenance strategy. So what strategies are there available? Well, in the terms that I'm using, there are only 3 generic maintenance strategies, or there's also a variety of tactics. If you do nothing else, you will inevitably operate in a world of breakdown maintenance. You'll run something until it fails, RTF, and then you fix it. And that's simple in that you don't need to do any planning, but it means you have no control over what happens or when it happens or how you get spare parts. It leaves you in a world of chaos. It can be expensive to fix things because they do more damage as they break down, and it'll cost you more to do the same repair because you have to get things in a panic. So people try to move away from that to do things in a controlled manner by planned preventive maintenance, where you define the tasks you're going to do, you do them at a certain set time, let's say every year, you strip the plant down, and you can, because it's ordered and pre-planned, you can make sure that you've got the people that you need to do the work and the spare parts and the tools all ready for it. So it gives you some control. However, it tends to result in over-maintenance because you're maintaining too frequently, and if you're working on your machine when you didn't really need to, you run the risk of introducing a fault that wasn't there before, so it can actually impair reliability. Really what you want to do is only maintain your machine when you know it needs it, because you've identified that there's an incipient fault developing, and so now you know it's the time to do the maintenance. And that's what condition-based maintenance or predictive maintenance is all about. The net result of that should be that you minimize the amount of work you need to do because you're only working on it when you know it's required. You minimize the cost, you maximize reliability. So condition-based maintenance has a lot of advantages. It's not necessarily appropriate to every single situation. If you want to decide rationally between these 3 strategies, there's a technique called RCM, reliability-centered maintenance, for analyzing each situation and identifying the best technique. It's a fairly heavyweight process though, so it's hard to justify on all your assets. And there's many other things, let's call them tactics, that you can do. Total productive maintenance, root cause analysis, proactive maintenance, for example. And RCM, as one of its overriding decision trees, has the recommendation that you should adopt condition-based maintenance if you possibly can. We can summarize the upsides and downsides of each of those 3 strategies in this table here. Now's not the time to go into it, but if you would like to get a copy of the slides afterwards, you'll be able to review all of those. We can simplify the arguments on those previous slides on this slide here. Why should you change from breakdown or routine PM towards predictive or condition-based maintenance? Well, simply in terms of cost. Rule of thumb that's quite often quoted is if you're currently operating a breakdown maintenance regime and it's costing you a certain amount, if you were able to move to a planned maintenance regime, you could probably save about half of the cost because you'll be able to plan things and do them more efficiently. If you can adopt a predictive maintenance regime, condition-based maintenance, then you can save up to 90% of the costs. I'm not going to guarantee those numbers in any one situation, but they're quite widely talked about as the sort of numbers that you can achieve. We talked earlier about the pressures to change. Why should you do anything? Well, the water industry, like many other industries, is under cost pressure. Customers demand lower bills. You're under pressure to become more effective, more reliable, to get more through your plants as more customers come online, to improve your reliability, to improve the service that you give to customers and reduce your maintenance costs, and actually to become more efficient in energy consumption, even without the cost pressures of wasting energy. The pressures on us all to achieve climate change targets and reduce our carbon footprint is high, and then specifically now spiraling energy costs are a massive incentive on all of us to try and do something different. The right kind of condition monitoring can help with all of these. To adopt condition-based maintenance, you need a means of condition monitoring, and there are a number of techniques around. Electrical testing, taking a meter and checking out your electrical panels, vibration analysis, handheld or permanently installed, acoustic emission, ultrasound, very capable technique, lubrication analysis, great technique, not particularly applicable for most water industry pumps, thermography, great way of seeing images of showing the temperature of your plant, motion amplification, sort of movie version of thermography in that you get some very compelling images, motor current signature analysis, MCSA, or same thing really, ESA, electrical signature analysis, and the latest generation of that brings some great new capabilities of automated diagnostics is model-based voltage and current analysis, or MBVI, which we're going to be talking about later. Of all of those, vibration analysis has been and still is the leading technique. What I'm going to suggest to you is that some of these newer techniques bring new capabilities and give you a reason for adopting condition-based maintenance now when it wasn't appropriate before. We've said that vibration monitoring is the most widely adopted technique, but condition monitoring in the water industry presents some particular challenges. For example, equipment can often be inaccessible, which makes it hard to go and take readings. You have multiple remote sites. If you're taking handheld data collection, you've got to send someone out there. That's a significant cost. If you've got unmanned sites, there's no one there to be familiar with normal behaviour, know what it sounds like or smells like. In some places you've got flammable atmospheres, and these days increasingly with inverter driven machines you have things operating at varying speeds and varying loads. Those things can make it more difficult to interpret vibration readings, and inverters can also, as a result of the distortions on the electrical supply, can create signals that are actually detected by vibration systems and can mislead the diagnosis that you make. And it doesn't help when you have lumps passing through pumps, variable density and so on. All makes it more difficult to interpret the results, makes vibration monitoring more difficult. But there is a technology that gets around a lot of those disadvantages and makes use of a sensor you already have installed on every pump, and that's the electric drive motor. Forget for a moment that it's a motor, just look at its construction. It's actually very well designed to be a sensor with lots of windings all very precisely located, and we can use that to tell us a lot about what's going on inside the machine. So if this motor is so wonderfully constructed to be a sensor, how does it actually operate as a sensor? Well, the first thing is that the motor current isn't just a fixed number that every time you turn your motor on you'll get the same current. The current, although you put the same voltage in every time, is affected by a number of different things. The first one is if you have a damaged motor, if you've got cracked rotor bars, for example, things that look a little bit like this in the structure, you get distortions on the current that occur at certain characteristic frequencies, and this is what conventional MCSA, motor current signature analysis, was all about. These days we're able to look at additional factors. If you have, let's say, a big misalignment on a shaft, you can put some very large transverse forces in that bend the actual structure of the motor, that bend the shaft, distort the casing. That can give very significant signals at a different frequency from the rotor bar defects. And then thirdly, the thing that's most relevant for a lot of what we do is that the load on a motor, the torque that the motor is having to put out, affects the motor current. You'll be familiar with the idea: if you put more load on a motor, it'll draw more current. If you put less load on a motor, it'll draw less current. So if you have a varying load, you have a varying current. And that's what modern MCSA systems or ESA systems are all about. But those three factors are not the only factors. In fact, they're not the key factor that affects the current drawn by a motor. The key factor, if you think about it, is the voltage. If you didn't have any volts, you wouldn't have any current. If you had volts of a different frequency, you'd have current of a different frequency. And crucially, in the sphere of condition monitoring, if you have a distorted voltage, you'll get a distorted current. And so if you want to do good condition monitoring and fault diagnosis, particularly automated fault diagnosis on your motor when in an environment of distorted voltages, such as an inverter driven machine, you need a technique that can deal with that, and that's what model-based voltage and current MBVI systems are all about, because they're identifying distortions of the current waveform that haven't been caused by distortions of the voltage. That means they must have come from the behavior of the machine, and that's what we want. So it's probably easier to understand these things and explain them by looking at a real example. So here is the current and voltage traces that we've taken just very recently at a water company here in the UK at a booster pumping station. You can see this is an inverter driven machine because these are distorted voltages and somewhat distorted currents. But it's hard to interpret these profiles just by looking at them. The system's done that automatically, and it's showing up here the overall, these four boxes here. This first one shows you the overall condition of the machine at the moment, and it's green. The next one is the predicted short-term condition, which means up to a month from now, that's green. The predicted long-term condition means up to 3 months from now, and that's green. And the fourth box indicates an issue with the electrical supply, and we'll look at that in a bit of a minute. How does the system identify these parameters here? Why is it green for the machine? Well, it's summarizing the way it's analyzed that by this bar chart here. The bar chart is displaying a whole load of phenomena that the system has identified. The 5 on the right with the pink background relate to the electrical supply. We'll look at that in a second. The ones on the left with the brown middle relate to the machine, there's maybe a dozen here. The system can detect around 40 faults, but it only ever displays those that are relevant to this particular machine. And you can see these are all low, things like motor unbalance, misalignment, motor bearings, motor foundations, motor transmission, driven machine, unbalance, misalignment, foundations, transmission looseness, and so on. They're all low, small bars. They're green, and that's what's driving the present condition. And because the system's keeping an eye on, are these increasing or are they stable, that's what it uses to predict the condition in the short and long term. The electrical supply over here, yes, we'll talk about in a second, but just draw your attention to, because we're measuring current and voltage and power factor, we know what the power is. And given an electricity cost, actually this one's already out of date, things have been going up so rapidly recently, we can see the total cost in this particular case. This pump is costing about £80,000 a year. I think that's probably out by a factor of 3 at the moment, given the amount that electricity prices have increased. So we can see what the total power, 66 kilowatts, and the cost £80,000 a year. What's more interesting though perhaps is, because we're able to detect the level of each of these faults, and because each fault in a machine takes a little bit more energy to drive the machine. You know, if I've got a really badly worn bearing, it's harder work to turn it. That's taking more energy. Faults are all like that. The system, because it works out the level of each fault and it understands the sort of amount of extra energy used by each of those, it's able to calculate for each individual fault the energy loss associated with that, and it's looking at the worst of those and saying, in this particular case, out of our 65 kilowatts, about 1.6 kilowatts is being wasted, and that's costing us about £2,000 a year. So we could take the view, the asset owner, operator, could say, well, I'm not predicting that my machine's going to fail in the next 3 months, but if it's costing me £2,000 a year, or with the new electricity price about £6,000 a year, it would be worth my while coming along doing some precision maintenance to get perfect alignment, to get perfect balance, all of those things to reduce my the levels of these parameters and reduce my energy cost. So this system is able to not only tell you how much power you're using, work out how much it's costing you, but it's working out how much you could save by doing precision maintenance. It'll tell you which of these faults is the thing to go for. So just to kind of build that in, the electrical parameters here, we can see current and voltage THD, total harmonic distortion, they're amber. You can see the 5 bars here actually are represented by these 5 parameters here: power factor, voltage balance, current balance, voltage and current THD. And the color codes there correspond to there. We're also providing other information on things like frequency, 48.33 Hertz, as we saw before. It's an inverter driven machine, and so on. So those all relate to the electrical supply. These two that are highlighted, corresponding to these 2 bars that are highlighted, that's just showing how these things are linked. The machine parameters we've already described are linked up here. So that's effectively covering how the whole system works. I described earlier that the water industry poses a number of challenges to vibration monitoring, which perhaps has been part of the reason for limiting the adoption of condition-based maintenance in the water industry. Some of those challenges were around difficulty of getting to the machine to take readings with vibration. With using the motor as a sensor, your readings are always taken in the switchgear, so it's always going to be clean, dry, safe area regardless of where the pump itself is. Inverter driven machinery operating varying speeds, varying loads, the current and voltage waveforms convey information about what the load and what the speed is, and so the systems automatically compensate for them. Electrically generated signals that can affect vibration readings, they're just part of the norm as far as MVVI systems are concerned, as are torsional vibration problems. So all of those problems go away when you're using an MVVI system. These model-based voltage and current systems come in a variety of different formats. In our case, we supply both portable and permanently installed systems, and it's often a good way of starting to assess this technology on your own machines by using the portable kit. But if you've got something you really want to know about and you seriously want to adopt condition-based maintenance, you're going to want to have 24/7 monitoring of the condition, and so that's what the permanent solutions are for. So in conclusion, condition-based maintenance has the potential to give you the highest levels of reliability at minimum cost of your business. To do condition-based maintenance, you need some form of condition monitoring. In the past, there have been some real challenges in the water industry, and that is overcome to a large extent by using the motor as a sensor which allows you to adopt condition-based maintenance even on assets that are really difficult using conventional vibration monitoring. And the right technology, the model-based voltage and current systems, the MVVI systems, also provide energy monitoring, identify the cost of the energy you're using, and identify the areas of energy waste, allowing you to target means of reducing that waste. And you can start with a portable test kit to prove to yourself that the system works on your assets before you commit to permanent installation. You're here at a conference to learn new things. There's no point learning new things if you then don't go and do something about them. So if this is at all interesting to you, I would suggest think about how you might go and deploy this in your own patch when you get back to it. If you're interested, Kemin Seo from TechPoint Engineering is in the hall today. You probably stand up now. If you want to look out for Kemin, go and talk to him afterwards, and I wish you well with all of it. Find him. So if there's any questions, please contact us or contact Kemin Seo, and I wish you all good luck with optimizing your maintenance strategy. Thank you.